Hi everyone! Today, let's talk about section 12.2, Classical Runge-Kutta method. The previous session suggested using more terms in the Taylor series representation for the unknown function y give more accurate results. But the necessary computation of derivative of f is often too difficult to make a higher order Taylor method attractive. Right? Do you remember last time? I can show you here. Just looking at this example, wow, the second derivative is quite long. Okay, so imagine if we want to have like more terms in the Taylor series, we have to keep like taking the derivative, higher derivatives. Well, this process could be complicated. Okay, so today we're gonna introduce the classical Runge-Kutta method. And it is the fourth order method. Okay, so what does that mean? What does fourth order method mean? If you can remember, the Euler's method, the error is a second order error. Okay, for the modified Euler's method, the error is a third order error. Okay, but the Runge-Kutta method is a fourth order error. Okay. And we know that if the order is bigger, then the error is smaller. Okay, so what it uses a linear combination of four function evaluations. First, let k1 be h times f of xi, yi. And then k2 is h times f of xi plus 0.5h and yi plus 0.5 k1. k3 equals h times f of xi plus 0.5h, yi plus 0.5 k2. Okay, k4 is h times f of xi plus h, yi plus k3. And then yi plus 1 is a linear combination of yi, k1, k2, and k3, k4. Okay, so this is the formula. Let's look at the example. So we want to approximate the following in initial value problem over the interval from 0 to 1 using the Runge-Kutta 4 method with h equals 0.5. Okay, so let's draw the picture here. So we have the interval from 0 to 1 and h equals 0.5, which means we divide it into two subintervals. Okay, so it's basically like two steps. And x0 is, so this is x0, this is y0, this is x1, x2, and we're looking for y1 and y2. Okay, so x0 is 0, y0 is 1. So far, so good, everybody? Okay, first step. Okay, step 1, x1 is 0.5, right? And then what is k1? K1 is h. By the way, h is the step size, which is 0.5. Okay, so h equals 0.5. We plug in k1 is h times f of x0, y0. So h is 0.5. F of x0, y0, that is, okay, let me write out. So f of x0 is 0, y0 is 1. Oh, what is that? Well, that is 0 squared times 1 plus 1. That's the same as 1. So 1 times 0.5 is 0.5. That is k1. By the way, when you work on these problems, try to write tiny, okay? Because each step we have to calculate k1, k2, k3, k4, and the yi plus 1. So we need a lot of space here. So k2 is then h f of x0, which is 0 plus 0.5 times h. So which we get 0 plus 0.5, h is also 0.5. And then y0 is 1 plus 0.5, k1 is also 0.5. So this is h is 0.5 times f of 0.5 times 0.5 is 0.25, and then plus 1, so 1.25. So far, so good, everybody? Okay, so we plug in it's 0.5, and then x is 0.25 squared times y is 1.25 plus 1. And what is this number? Okay, calculator here. 0.5, oops, times parentheses 0.25 squared times 1.25, then plus 1, close parentheses. Oh, we get 0.539065. 0.539065. Okay, that's K2. Well, K3. What is K3? H times f of xi, which is 0 plus 0.5. H is 0.5. And then yi is 1.5 times K2. Okay, so in our calculation, let's see, we get 0.539065. So if we have a lot of numbers, it's okay to keep 5 decimal places in the calculation. Okay, so let's see. This is 0.5, and f, 0.5 times 0.5 is 0.25 square times the y. The y is actually this 1 plus 0.5 times 0.539065. Okay, and then plus 1. Okay, because it's x squared times y plus 1. Okay, let's calculate it. So we can use the previous line, but now here we place it by 1 plus 0.5 times our previous answer. Okay, so, and it's enough to keep 5 decimal places. So we get 0.53967. So this is K3. How about K4? K4 is h, f of xi 0 plus h is 0.5. And then yi is 1 plus K3 is 0.53967. So h is 0.5. So now the x we plug in 0.5. So 0.5 squared times 1 plus point that. So it's 1.53967 plus 1. Okay, what is this answer? So we can copy the previous line, but here this is 0.5 squared, and then change this to 1.53967. Okay, and we get 0.69245. Okay, and we can round up. We get 0.69246. So far, so good, everybody? Okay, so once we get K1, K2, K3, K4, then Y1 equals Y0. Y0 is 1 plus 1 over 6 times K1, which is 0.5, plus 1 over 3 times K2, which is 0.539065. And then plus 1 over 3 times K3, which is 0.53967, plus 1 over 6 times K4, 0.69246. Okay, let's see, what is this number? Yeah, the process is actually quite long, so I want you to like organize your data, write it very carefully, okay? So yeah, because sometimes if we read the number wrong, then whatever after is gonna be all wrong. So especially when we have a lot of data, it's very important to organize in a very clean way. Okay, so we have that number, we can copy it here. Then we don't need to type it again. So plus that number divided by 3. And then plus the next number, which one here? This one, right? This number divided by 3. Okay. Sometimes we might have round off error, but it shouldn't be so big. Okay. So the answer is 1.55832. And that is Y1. So 1.55832. Now you can compare this method and the Euler's method. Ooh. The Runge-Kutta method, even though we don't need to take so many derivatives, but each step we actually need to compute 5 values, K1, K2, K3, K4, and Yi. Okay, second step. That is why this interval we only divide it into 2 subintervals. Okay, so step 2. Let me see, do I have enough space here? Okay, good. Do you still have enough space? I hope so. So here, x2 is 1, right? And k1 is h times f of x1, y1. H is 0.5, and then f of, what's the point? This is the point we're gonna use. 0.5 and 1.55832. So that equals 0.5 and then 0.5 squared times y is 1.55832 plus 1. Okay, what is the answer? So calculator. Let's copy this guy. Okay, what do we need to change? Oh, change this to 5832. Right, everybody? Okay, so we get 0.69479. Alright. And K2. K2H is 0.5, right? So okay, we can also put H, and then we have X1, which is 0.5 plus 0.5H. So 0.5, but H is also 0.5. And then we have Y1. Y1 is 1.55832 plus 0.5 K1. K1 is 0.69479. Is that okay, everybody? We are using these formulas. Okay? By the way, those formula will be given in the exam. So you don't need to memorize it. Alright, so H is 0.5, and then F, we have, this is actually 0.25 plus 0.5, 0.75, right? So 0.75 square, that saved me some work to type in the calculator. And that one is 1.55832 plus 0.5 times 0.69479. Then plus 1. Okay, what is that answer? Calculator here. So 0.5, we can also copy and paste here. Then we don't need to retype everything. This becomes 0.75 squared, and then this number plus 0.5 times 0.69479. Okay, so the answer is 1.03598. So far so good. This is K2. So we still need to find K3 and K4, and then we can find Y2. Yeah, this process is quite long compared to what we have done before, right? Okay, so and we have to be patient and calm down. Okay, sometimes if you need a break, you can like pause here, maybe go to the restroom. Yeah, go to the restroom and wash your face. Okay. Okay, so let's continue. So that is almost the same as before, but replace K1 by K2. So almost the same as the last step, but we place K1 by K2. So we place 0.69479 by 1.03598. So almost the same, but we place that by 1.03598. Okay, what is that number? Alright, so it's almost the same. So we can go back to the previous line and change that number to 1.03598. Okay, so we get 1.08396. 1.08396. So far so good, everybody? Okay, that's K3. We still have K4. K4 is H, and then we have X1 plus H. So not 0.5H. Okay, so this is different. So this guy is 1. And then we have the YI. Y1 is 1.55832 plus K3. K3 is 1.08396. So that equals H is 0.5. And then 1 squared is just 1 times 1.55832 plus 1.08396 plus 1. Okay, what is that? Okay, so we can copy it and paste here. 1 square is 1, and here no 0.5 there. 1.8396. Okay, So the answer is 1.82114. Okay, those are the K1, K2, K3, K4. Y2, finally, yay, is Y1, 1.55832 plus 1 over 6 times K1, 0.69479 plus 1 over 3 times K2, which is 1.03598 plus 1 over 3 times K3, 1.08396 plus 1 over 6 times K4, 1.82114. Okay, put this in our calculator. So what is that? First, we gotta need this number plus 0.69, where are you? Here, over 6, and then plus this number. You can also go up to your actual calculator. So by the way, when you're watching the videos, I really hope that you actually type those numbers and calculate in your calculator, right? Because sometimes you watch me do it, and whether you can do it, we're using a different calculator, right? Maybe the button are different. So I want to make sure you know how to do it on your own. Okay? So the answer is 2.68429. 2.68429. And yes, that is our final answer. Okay? So 2.68429 is our Y2. Whew, so far so good. Yes, that's the Runge-Kutta method. And yeah, we have to find K1, K2, K3, K4, 4 functions evaluations. And then the yi's is going to be a linear combinations of those. Okay? Yes. So only, see, the 2 steps is already take us 20 minutes and a whole page. Okay, how to use MATLAB. Okay, so example 5, apply the Runge-Kutta method to approximate the solution of the initial value problem over the indicated interval. So this function is like what we had last time. Runge-Kutta method change the syntax to RK4S. Okay, and we will see 10 points, and we also get these values, and we can plot the curve, and this is the curve. Let's do it again in Octave. Okay, here, let me copy the syntax here. Okay, so or you can use the previous ones, just change these numbers, just change these letters to RK4S instead of Euler, okay? And enter. So we get minus 1.05446. And if you can remember what we had before, let me go up and then to show you what we had before. The Euler's 2, not this one. Okay, this is the Euler's 2 using like 100 steps. You can see close enough, right? And if we use Euler's 2, let's compare. Okay, if we use Euler's to 1,000 steps, what happened? Ooh, that's quick. See, minus 1.08. And let me remind you again, 10 steps, we already get 1.05446. How about Euler's 2 using 5,000 steps? I don't know how long it will take. Maybe, let's see. Oh. 1.05823. So it's about 1.5058. Okay. If we use the Runge-Kutta method, let's do 100 steps. Ooh, you can see we also get 1.058 there. Okay, so keep in mind the Euler's method is a second order approximation. Modified Euler's method is a third order approximation. The Runge-Kutta method is actually a fourth order approximation. So ideally, in general, the Runge-Kutta method will be more accurate. Okay, so let's check our example. Okay, so let's check our work. We have spent 20 minutes on this example. Let's check it and see whether we're right. So, Runge-Kutta method, and here we're using n is 2. Yeah, only 2 steps. And while 0 is 1, the interval is from 0 to 1. And the function is x squared times y plus 1. Okay, see? 1.5583, 2.6843. Yeah, see, we get those answers. So our answer match. Okay, great. All right. Yeah, every time when I use the MATLAB to check my work and I get the answer correct, I feel so relieved, because imagine if you get the wrong answer, they don't match, then you think, oh, look at this whole page, where is my mistake? Then we have to search from the beginning to the end, each line, each number carefully to find out the mistake. Yes. Okay, interesting, right? So that is the Runge-Kutta method. And that's it for today. So chapter 12, we only cover session 12.1 and session 12.2. That is the Euler's method and the Runge-Kutta method. So those methods help us to solve ordinary differential equations, first order ordinary differential equations. Okay, so that is like remember we talk about linear algebra and differential equations, and we learn about differential equations. So we know there's many differential equations we were not able to solve. But here we can use numerical methods. We can use Euler's method and the Runge-Kutta method to help us to approximate the solution. Okay, and when we increase the number of subintervals, of course, we can get a more accurate answer, as close as we want. Okay? All right, so have a nice day. Bye.